All right, the next characteristic of polygons that we're going to look at is called area. And area, as we've discussed before, is the amount of space on the inside of a polygon. Right, the amount of space on the inside. Now, once we discuss polygons, we'll actually look at another shape called circles. They're not technically polygons, but they can also have area because they have space on the inside. Area is measured in what we call square units. We've talked about this when we did units previously. We have square inches, square feet, square meters, and those units are simply just a square, 1 by 1 square, using whatever unit we're discussing. If we're working in inches, then it's a 1 by 1 square, okay? 1 inch by 1 inch. And the rectangle is really the basis of most of our area formulas, okay? Maybe not so much for the circle, but the other ones that we're going to see today, the rectangle is really the foundation. It's the basis. Because every rectangle can be made up of 1 by 1 squares, and they fit in there really nicely. Okay, especially this little rectangle that I have drawn up here has 2 rows of squares and 4 columns of squares. Okay, so in this particular one that I drew, the width is 2, I'll call them inches, but who knows, it could be centimeters, it could be anything. And the length is 4. And so when you sort of split this up, you can fit 2 rows of 4 columns in that space. And so the total area is just the number of little 1 by 1 squares that fit in there. So the area in this case is equal to the the product of those two. If you count them up, there's 8 of them in there, right? And that's the product of the rows by the columns. And we would call those 8 square inches, okay? And of course, with any rectangle, and you can kind of see from this example, the area is going to be the number of rows multiplied by the number of columns, or you could just say the length times the width, or width times the length, okay, interchangeably. So the area in general for a rectangle is length times width, okay? And that's going to be super important as we go through the rest of these examples, so we know that the area is the length times the width for a rectangle. Now a square is a special case of a rectangle. It's a rectangle when not only opposite sides are equal, but all 4 sides are equal. And so whatever that side is, if you think about the area as being, again, the length times the width, well, it's going to be S times S. The length and width are the same for a square. And so we would say that the area is actually the side squared. So, for instance, if I knew that if the side length was 5 feet, then I know that the area is going to be 5 squared, which is 25 square feet. So I'd be able to fit 25 1 by 1 squares, 1 foot by 1 foot squares, in that 5 by 5 square, okay? All right, so squares aren't too bad. Just square the side. Makes sense? Triangle is fascinating to me because you can take any triangle. It doesn't matter whether it's scalene, isosceles, equilateral, acute, right, or obtuse. No matter what size, what shape, no matter what shape triangle you have, you can always build a rectangle around it. Okay, and you can kind of see on this example, I've got the black triangle in the middle with a red rectangle kind of hovering around it. And when you do this, you can kind of see that the triangle is exactly half the size of the rectangle. It takes up half the space. Now I can argue it this way. I've drawn in here a vertical line from the top corner down to the bottom side. The bottom side we're going to call the base here. And what's interesting is that vertical line separates us into really 2 different rectangles, right? A narrow one on the left and a bigger one on the right. The narrow one half of the space of that narrow rectangle is inside the triangle and half of the space is outside. You can see how that the side of the triangle kind of cuts that rectangle in half on a diagonal. On the other side here, the same thing happens, right? You have half the space of this rectangle inside the triangle and half of it on the outside the triangle, okay? And so that means that the triangle must take up half of that space. So if the triangle takes half of each space, then it takes up half of the space as a whole, okay? And what does that mean? If it takes up half the space, then it must have half the area. If the area of the rectangle, this red rectangle, if that's length times width, well, the length is the base here of the triangle and the width is the height, right? So the area is base times height for the rectangle. That means the area for the triangle must be half of that. So area is 1/2 the base times the height of the triangle, okay? And so if I had a triangle and I knew that the, let's say the base was, I don't know, 15 centimeters, and if I knew the height was, let's say 8 centimeters, then the area is 1/2 times 15 times 8. I could do 15 times 8 times 1/2, or I could do these in any order, actually, right? I like to do the half times any even number if there is one. Makes life a little bit easier. So 1/2 times 8 is 4, and 4 times 15 is 60. So that's 60 square centimeters for that area. Okay. Okay, so that's the area of the triangle. Now the area of the whole rectangle, which is not what I was asking for, is double that, which is 120. Okay. So that's cool. That's the area of the triangle. It's 1/2 the base times the height. The area of the parallelogram is interesting. A parallelogram is a quadrilateral, means it has 4 sides, and opposite sides are parallel, okay? When you have that situation, they are also equal in length. Opposite sides are, just like a rectangle, except it's like a rectangle on an angle, sort of. You don't have all 90-degree angles. But what's interesting is on a parallelogram, you can see I've cut off using a vertical line there, just like I did with a triangle. I cut off a little teeny slice of a triangle over here on the left side, and if you were to remove that and insert it over on the other side, it would fit perfectly into a rectangle, right? So this is really a rectangle with a little sliver triangle cut out and slid over to the other side. Now, if you think about that, the area of the rectangle is the base times the height, or the length times the width. If you take that little slice of the triangle off and move it over here, you haven't changed the area, you've just moved where it is, right? The actual space on the inside hasn't changed. And so the area of the parallelogram is going to be the base times the height. Okay? Yeah. It's really 2 triangles put together in some sense, right? You could cut that into a pair of triangles, and 2 triangles would be double this area. So anyway, so the area is the base times the height. It's going to look a lot like the rectangle formula. Okay. So all 4 of these really are built. Off of the rectangle, and so they're, the areas are kind of straightforward. They kind of make sense based upon the rectangle. Now these 4 formulas I do not plan to give you on the test. I do expect that you guys will know these 4 area formulas. I also do not plan to give you perimeter formulas on a test. So those are ones that I do want you to know coming up. Okay, now the other one, the other shape, the other polygon we're going to look at is called the, I just lost the name of it. Trapezoid. I don't know why that was escaping me. Trapezoid. Alright, so let me draw up a trapezoid here. I'm going to take a little bit more space for this one. And I believe I spelled that right. The trapezoid is a quadrilateral again, but this time it only has two sides that are parallel. Okay, the other two sides are not necessarily. So a trapezoid could, look something like this. I don't know. None of those corners are drawn or intended to be 90 degrees. They're all just all over the place. But there are two sides that are parallel, and the other two are just there. They're not necessarily parallel. If they were parallel, it'd be a parallelogram. So it's not. So that's a trapezoid. Now we can actually find the area of a trapezoid. This one's kind of cool. And the trick on this one is to build another rectangle in there. But the rectangle we build uses the average of the two parallel sides. Okay? So if you take those two parallel sides and take their average, you're finding a length that's halfway in between them. So if you imagine a length that's halfway in between them, it would have to end halfway between, if I draw this edge straight down here, or a height straight down, it would start halfway across there, and if I draw this straight down, it would stop halfway across that gap, and that would be the average. So it would come up and it will actually intersect the midpoints of the two non-parallel lines. Okay? So the average of the two parallel lines intersects at the midpoint of the two non-parallel lines. Okay? And if I then use that as my length for a rectangle, and I create the rest of the rectangle from that, it might be a little bit hard to see from this diagram, but oops, it's just really because of the thickness of the marker and the fact that I drew that angle kind of sharp. That's not too bad. Okay. Well, what ends up happening is, I'll show you on the left side because the sizes are bigger. And get rid of some of this other marking here. Distracting. There we go. Okay, so what happens is this little triangle down here on the lower left, I'll shade it in, is equal size. That one's in the trapezoid. That one is equal size to the one up here in the upper left that's outside the trapezoid. Okay? Same thing over here. This one little sliver of a triangle that's inside is equal size to the one that's on the outside above it. And so if I were just to cut those off and splice them up above, I create a rectangle. And the rectangle, this rectangle then has a length that is the average of the two parallel sides, okay, of the trapezoid. So what I need to do is get a formula for that average. Okay, so here's how we do that. The base here, the long side of the trapezoid, I'm going to call it A. And the short side, I'm going to call it, that's just the short side of the trapezoid. That doesn't go all the way across. That's going to be B. I guess it really doesn't matter which one's A and B. And so the length of that rectangle then, which is the average of the two. Now, how do you average two numbers? You add them up and divide by 2, right? The average of any number of numbers is the sum divided by the number of the numbers, right? If you want to find your test average on 3 tests, you add the 3 test scores and divide by 3. Well, here I'm averaging 2 things. So I add them up, A plus B, and divide by 2, okay? Now, the way that the formula is going to represent that, instead of dividing by 2, they're going to multiply that by 1/2 instead. Looks a little bit nicer. So we're going to say 1/2 of a plus b. That's the average. Okay, that's the average of the two. And so this would be the length of the rectangle, and then the width of the rectangle is the height, which I already kind of cut and then erased, the height of that trapezoid. Okay, this is a 90-degree angle here. So the area of trapezoid is going to be the product of the length, which is this 1/2 a plus b, that's my length, times the height, or the width. So length times width, which is h. Okay, so again, it's the average of the two lengths times the height. And the formula that you actually see in the book and that you'll see in my math lab, the more common formula is just to interchange the h with this quantity. Multiplication is commutative, so the order doesn't matter. So we usually write it as 1/2 h times a plus b. Okay. So if you're given, three of those three pieces of information, you can figure out the area from there. One time I was getting concrete poured for my driveway, and my driveway is the shape of a trapezoid, which is kind of interesting. And the contractor who came over to give me an estimate on the price of getting that concrete poured took a few measurements and had a calculation way faster than I would have, because he used this formula, but he used it in such a way that was just kind of intuitive. And I didn't even think about it at the time. Even knowing the formula for a trapezoid, I wasn't thinking about it as a trapezoid. I was thinking about it as like a combination of triangles and rectangles. I was going to break it down and take a whole bunch of little measurements and try to figure out each individual trapezoid and rectangle and add them up. But he had a way faster way to do it. And I'll just show you briefly what his technique was. After he came up with a solution, I realized what he did, because he was kind of talking through it verbally, and he beat me to it. And I was shocked that he got me on that one. I'm like, man, I should know that, but I didn't. But anyway, so my driveway it comes off of the road, and it kind of goes on an angle because my house is offset from the culvert. So the ditch goes across, there's a culvert, and my house is shifted over in front of the ditch more, so we had to come in off an angle. And it's the driveway is actually slightly narrower at the road than it is at the house. And so if my house is over here, just a rough rectangle, it's not quite, but close. And the driveway kind of looks like that. And it is a trapezoid because the road edge and the house edge in front of the garage are parallel. That's all you need, are two parallel lines. And I didn't even consider that was the case. Like, I was just going to try to chop this up into triangles and rectangles and make it work, or make one big rectangle and then cut off the triangles. That's what I was thinking in my head. But what he did is he just went up to the house, measured this distance here, which I think is 30 feet, and he measured this distance here, which, if I'm not mistaken, is, I was going to say 12 feet, but yes, I think it's 12 feet. I don't know, this was like 6 years ago or something, 7 years ago. I don't know. It's been a while. But anyway, it's about 30 feet by 12 feet as those two. And then the distance, and all he did, he took those two measurements, which are simple measurements, just with a tape measure. And then he measured one other distance, which is simply the distance from the house to the road, or the edge of where that was going to go. And it was kind of weird that he didn't have any other measurements. That was it. And that was a 90-foot measurement. The house is about 90 feet off of the road, or it might be more like 100 feet off the road, but there was a little gap where we couldn't have the driveway go all the way to the road, but it was close. It was 90 feet, I'm pretty sure, was what it was. And so his calculation in his head, he just averaged the 30 and the 12. Well, what's halfway between 30 and 12? If you add them up, you get 42 divided by half, you get 21, right? So he averaged those and real quick got 21 for the average, multiplied by the 90. And he did that in his head because 9 times 2 is 18, and 9 times 1 is 9, and you tack the extra 0 on. It was right around 1,890 square feet for that driveway, right? And that's really all you have to do. You average the two parallel sides and multiply by the distance between them there. And that is, and even if it goes outside of the trapezoid, it doesn't matter because the formula is the same either way. And so, if you use the actual formula here, it's 1/2 times the height, which is 90, times the sum of those two, which is 12 plus 30, right? But he didn't even really need the formula. He just knew instinctively that it was the average of these two numbers times that one. And that was good enough. And in his head, it was super quick arithmetic, and he got me on it. So anyway, I'm a little competitive, and I was hoping to win that one, and he had the answer well before me. And I'm pretty sure it was 1890, or it was very close to that. And then, of course, now here's an interesting idea. So this gives you the area, right? The square area. But that doesn't give you the estimate. You still have to know how much the concrete costs, right? And so the concrete, I don't remember exactly. I think it was around $7 a square foot or something like that. Is that right? Could it have been $7? Maybe it was $6, $4? No, I don't remember. Oh my goodness, it's been too long. Let's just say it's $5 because it might make this work out nicely. So let's say it's let's say we want $5 per square foot. Then the actual cost of that would be, you take the number of square feet and just multiply by the cost, right? The $5. So multiply that by 5, 0, that's 45. 5 times 8 is 40, and 4 is 44, and 5, 9, $9,450. Okay, so it's a nearly $10,000 driveway. I feel like that's high. It must have been more like $4 a square foot, something like that. It was, concrete ain't cheap, right? That's expensive, but and that was just for the driveway. We also put a walkway around the back and a patio on the back, and we had to have the garage floor poured and the basement floor. Cost that up. Anyway, so that was the driveway. I do feel like that's a little high. But anyway, just for an example, so you can kind of see, kind of how that plays out. And of course, the instinctiveness is the important thing there. You can follow the formula, but just to be able to do that quickly, it's kind of cool. It's kind of a neat experience that I had.